Hello everyone. Hi. Uh, could you please comment on the chat in case my video is visible and you're able to hear me properly? Awesome. Awesome. Yeah. So I think let's start. Uh, yeah, my screen should be visible now. Just message on the channel in case it isn't. Sure. Let's start. So, okay. Hello everyone. I am Aayush. I am really delighted to be here. I work with a company called Plivo as an engineering manager. I work with the messaging team there, and we at Plivo are a business communications platform wherein we provide APIs and products to our customers who are essentially businesses trying to reach out to their end users. For example, an Uber, which is a ride-hailing app trying to reach out to you with an OTP SMS or contacting you via WhatsApp, is a potential customer for us. So we help simplify business communications. Today, I'll be talking about an optimization saga with Go, which is our engineering team's journey trying to optimize our services, our platform towards reduced costs, better application performance, and higher availability. Cool. So, think I personally love trekking, and I am a big foodie. And this is the link to connect to me on LinkedIn in case you would want to have any questions post the talk. You can also reach out to me on LinkedIn. A little background on what exactly did we find ourselves into. So during the lockdown, many of the businesses were forced to go online, and companies had to essentially embrace remote work, which basically meant increased traffic for SaaS companies and products like ours, which are essentially you have a lot more need to communicate with your end users, your employees, your stakeholders in the business. So here are the few considerations we had to take in order to be able to say that our platform is ready for the scale we are about to witness. We wanted to improve application performance, reduce infrastructure costs, and the underlying theme of doing so, we wanted to measure what we wanted to improve. Right. So for that, for example, in the application performance section, we started with adding more granular observability, which includes things like distributed tracing. We started measuring and sampling P99 latencies. So out of 100 requests, what are the 99 top 99 requests slower than a particular time? That's the P99 latency. That's what the slowest of the slow requests we started to track. Also, as an engineering unit, we were tracking a ratio very closely, which is team's revenue over the cloud costs, right? So we have various mechanisms on public cloud infrastructures to be able to track cloud costs via budgets, cost tags, cost allocation tags, etc. So this ratio we try to keep within a certain range for all new features, functionalities, and business operations. So this is what the background for the entire story is supposed to be. In terms of the platform setup, our services are written in Golang. We use Elasticache with Redis for caching. We also believe strongly in the tenet that whatever does not need to be processed in real time shouldn't be. So we use asynchronous message processing quite heavily and use AWS SQS for that. We use Postgres for persistence and ECS, which is AWS Elastic Container Service, to be able to do service orchestration. Right? This is a background essentially for what tools and technologies we use. We started with the standard optimizations, right? You start by auditing your application calls to the data store, which are essentially going to be the first areas of bottleneck. You try to figure out your query patterns, look at performance insights of your different queries, try to run explain, analyze commands onto your select statements, try to figure out whether your queries are really efficiently executed on the database server or not. If they aren't, you need to basically start creating database indexes, audit existing database indexes, whether they are being used. If they are unused, you would want to prune them, remove them altogether. Then your application interaction with the data store can be in multiple ways, right? A naive way would be to, for each incoming request, you create a new connection with your data store. And then once the request is done, you terminate that connection. Rather than that, in a microservices architecture, what would really help is a connection pooler, which sits in between your application and your data store and can limit the number of open connections that you are trying to have with your data store. This also gives ways to control the load on your database so that you can prevent out-of-memory crashes, database being unresponsive, etc. Other things we started looking into were prepared statements, which is nothing but a pre-compiled SQL statements that the database server does not need to reevaluate on every incoming request. Then CQRS stands for Command Query Responsibility Segregation. We started looking into ways or trying to identify what our business use cases were, what kind of workloads were we running as well. Right? Was it a read-heavy workload? Was it a write-heavy workload? And based on that, we tried to segregate the requests going to the right target. For example, all your read queries should ideally go to a reader instance in your database cluster. So that's what we started doing. We leveraged a whole lot of caching at places where business use cases allowed it. Caching essentially helped us reduce load onto the database further. Then in order to be able to deal with traffic spikes, right, as you can imagine, messaging is not a consistent load kind of a scenario, right? Messaging would be very spiky, right? So in order to be able to scale applications better according to the spikes, but also keep costs in check, we fine-tuned our auto-scaling policies quite a bit. And then for asynchronous message processing, the message queues that we were using, the managed queues essentially have pricing which is per request. So if you want to continue to check whether there are new messages available to be processed or not, you have to make poll or you have to poll the queue. Long polling is nothing but spacing those polling requests out so that you are reducing on the cost, but still being able to fulfill your asynchronous processing needs. I'll take a pause here just in case there are any issues in terms of. So there's someone saying can't see my screen. Is that so? Okay. I think I'll go ahead then. Sure. I think my screen is visible, but someone said that it isn't. We'll just check once again. Yeah. Let's move on. Okay. Sure. So these are all the standard ways that you usually go for optimizations for your services. Now comes the interesting scenarios, right? These are the standard ones. Now we have certain specific ones to our use cases, right? After adding a lot of distributed tracing, understanding what kind of workloads we were having and what were the real bottlenecks, we quickly figured out that when you are making a lot of small requests to the data store and back, even if you are inside a private network in a VPC in a cloud setting, you would still find many a times that the network round trips are your bottlenecks, right? And this was a very common pattern across services, across different kinds of workloads that we were having. And something needed to be done for it, right? We had a lot of small queries which were independent of each other, part of the same business flow. And we wanted to find a way to be able to optimize on the latencies or the response times in that flow, right? So we leveraged a concept called query batching. It's a concept that is applicable irrespective of the kind of data store that you're interacting with, as long as you're okay with certain data eventualities. For example, let's say you have this service, you have small commands or statements to be run on your database server. One way is to you initiate a request with command number one. You make the request onto the data store. All of this will happen via the network. All of this will include the network round trip. The response will also obviously come via the network to you, and you will basically incur a network latency. What if you have command 2 to command n, part of the same business flow? They are independent of each other, right? You would want to reduce on the number of network round trips required for getting the response for all of these. So this is the overall basic concept that we leveraged across data stores, not just for caching, but also for SQL queries as well. So there is something called query batching, and it's not very difficult to implement. It's a straightforward enough concept, but has certain downsides. Like, for example, you won't be able to do things like read after write, right? Because if you're trying to read a value that you've just written as part of your batch request, that would not be good. But otherwise, anything which does not require atomic transactions here on the data store, you can combine them into a single network round trip, and all the responses for each command will be returned to you sequentially. So you can basically in the response go like first entry in my response is the result for command one. Second entry is the result for command two, and so on. We were able to actually reduce the round trip times quite significantly. And in terms of impact, we had a 36% improvement in P99 latencies for such workloads. Along with that, the other benefit here was that the number of database operations per second increased dramatically on our data stores. Why is that so? Essentially, with all individual requests, database server also needed to cater to IO requests coming in from the wire, trying to understand that request, execute it on the database server, respond back to the wire. All of that requires IO and consumes resources on the database server side. When the round trips are reduced, the database operations per second that the database server can now handle increases drastically. Right? So with the same amount of resources, you are able to serve even higher traffic. Right? An important thing to note here is this is essentially for independent queries where atomicity is not required. And we had such use cases in the read heavy workloads, which is why we were able to leverage this concept there. Right. The other aspect of the concepts we leverage to be able to improve on our cloud costs. So the previous one, we understood how we went about performance and reducing latencies. The second approach that we are going to talk about is about cost efficiency. How do you reduce cloud costs? Right? So as I mentioned before, we use asynchronous message processing quite a lot in our use cases. Asynchronous message processing, we are using via managed queues on AWS, which are SQS queues. There are a bunch of things to keep in mind while you have a high volume business use case or application interacting with these managed queues. Right? You have to understand the cost implications of these managed services as well. And that also enables you to be able to model your application in such a way that you can actually go about reducing your costs. Right? Let's understand some semantics around how SQS pricing works so that we can move ahead and see what the cost optimization was. Pricing for SQS is based on the number of requests you make to SQS. For example, you want to send a message to the queue, that's one request. You want to receive a message from the queue, that's one request, and so on. Every such request, every such action is essentially billable. One request that you make to the queue can have a maximum of 10 messages and a data size of up to 256 KB. But even so, each 64 KB chunk of a payload is billed as one request. So even if you try to combine your requests, a bunch of messages together, each 64 KB chunk will be billed as one request. So you can imagine for every message, the number of requests you're having to make to SQS. And in case you are in a high throughput, high volume, or a high traffic environment, these costs would very quickly add up. Right? Now, how do we go about reducing costs here? Instead of actually trying to make one request per message that we want to send and receive via the queue, we have a leeway of combining 10 messages into a single request and be able to reduce our cost by 1/10 by doing so. Right? This would definitely come with a cost, but let's understand the approach first, and then we'll talk about the costs associated and downsides. So we started with a very simple approach of client-side buffering. So imagine that imagine this to be a simple wrapper library on top of the AWS SDK in Go, and the service is using this wrapper to interact with the Amazon SQS service. How does this work? You will have a bounded buffer available to each service. This buffer is nothing but an array where you can keep all the incoming requests that you want to actually send to SQS. Right? This buffer has a few configuration parameters, right? One configuration parameter is around when do you dispatch, right? Once the buffer, let's say the buffer is full, at that point, you would ideally want to send the requests in batches to the SQS. Or you say that you have a number fixed in your mind that as soon as you have 10 requests in the buffer, you want to send those requests over to SQS. Okay? Buffer size and the batch size are different. Buffer is a bigger entity available to the service in memory. Batch size is fixed to maximum of 10, which is the batch size accepted in SQS. So once the buffer, let's say the buffer size is 1000, you will be able to send only a maximum of 10 requests in a batch in a single request to SQS. Right? You will need to understand when to dispatch, how to dispatch these messages from the buffer to the service, to the SQS service, right? So these are the configuration parameters which help us do that. A timer parameter, which we can configure saying something like, wait for 250 milliseconds, and after that, whatever number of requests are there in the buffer, send them to SQS. The second configuration parameter is around what is the buffer size that I want. And as soon as the buffer is full, I want to send those requests to SQS. So these are the two configuration parameters we used and kept the entire system pretty lightweight, with the downside, of course, being that if the service crashes, the in-memory buffer that we have will be lost, and your application needs to be intelligent enough to be able to retry those requests, right? In our use case, this was not a challenge, and this was not a highly critical system that we were operating. We had other mechanisms to be able to recover in case a service goes down. We also actually built in graceful shutdown within this application library wrapper as well. How you get a int signal from your service orchestrator whenever the service is about to go down. Handle that by clearing out the buffer at then and there before the application stops. So those kinds of checks we have incorporated within the library itself. But in case there is hard stop or immediate shutdown for a service, there will be at max buffer size number of messages that will be lost. And there has to be other recovery mechanisms in the application to be able to recover from that. Okay. But in terms of impact for this, we were able to reduce our SQS costs pretty drastically, right? This is almost like a 5 to 10x sort of improvement in terms of cost, right? Because instead of making one request, sending one message as a single request to SQS, we are essentially sending 10 requests at a time whenever they are available. Right? So this was the second interesting use case. Now we ventured into a point where we wanted to push the boundaries of what optimizations we were able to achieve for certain hot path applications / components. Right? Here we had a scenario where you have a very large data set and you want to do an existence check for an item. Right? You want to get the answer that this given item is definitely not in the given data set, or you want to get a probability of how probable is it that this item is present in this large data set, so that I can actually save on to a bunch of downstream operations. Right? All of these are probabilistic means of getting answers to your queries, right? You have your deterministic means, which is, let's say, given a hash map, tell me whether a key exists in that or not, or get me the value corresponding to that key. All of these are deterministic data structures. We ventured into something called probabilistic data structures. Right? They provide you an approximate answer to queries about large data sets in real time. Right? Wherever an approximate answer is good enough for you to be able to decide whether you want to, let's say, proceed with one application flow or the other, at those places, probabilistic data structures are pretty useful. Our use case will fit well into a probabilistic data structure called Bloom filter. Okay? Bloom filters provide you a very space efficient way to verify whether an entry is certainly not in a set. Right? So imagine in terms of use cases, let's say you are on a blogging platform like medium.com. The blogging platform wouldn't want to show or recommend to you articles you've already read. Right? How could they do it in a very space efficient way? Bloom filters could be a solution. You have a huge database of malicious URLs available to you in a crowdsourced version. And let's say you are building your own browser. Before a user actually goes out of the browser over to the domain name servers to get to the actual website, if you had a way to check whether a given URL is already supposed to be or known to be malicious, you could easily prevent the further actions by the user towards that URL. These are the kinds of use cases that Bloom filters are suitable for. And under the hood, if you want to understand how these work, you are looking at a simple array of bits or booleans, right? And you have k number of hash functions that you use on each entry that goes inside the filter. Right? Imagine there is a word called Bloom, and you have an array of booleans. That Bloom filter, that word Bloom, will go through, let's say, one hash function, which gives it an index. Let's say you have a filter of size 10, and after running the hash function on the string Bloom, you get the index 2. You will go and set that bit or set it to true, essentially. What this means is the next time you want to see whether Bloom string exists in the filter or not, you will pass it through the same hash function and see whether the corresponding index is set. If it is set, then probably your item is there in the Bloom filter. If it is unset, then definitely your item is not in the Bloom filter. Right? So you can, I think, visualize this in this naive implementation as well. Here, if you see, we are using a single hash function to be able to get to an index of the bit array, and we will just set the value of that index to true. Right? Bloom filters also have a concept of probability or tolerance levels for false positives. So you cannot guarantee that another word called apple will not also hash to the same same index. Right? So there is a possibility of false positives, but no possibility of false negatives, which is why Bloom filters have a very niche use case, but for the use case that they solve, they are vastly more efficient than any other deterministic data structures you can think about. Okay. I'll just take a small pause here in case. Okay, I think don't see any other questions here. Cool. Then I'd like to part with the interesting use case that we are trying to solve here. Interesting problem that we are trying to solve with this approach. Most of us might be aware about the cache aside pattern, right? If not, I'll just go over it briefly. Your application requires a data point or some piece of data. It goes to the cache and figures out that the data is not present in cache. Then application queries the DB, reads the values, sets the value in cache, and then returns the response to the application user. This is in general a cache aside pattern. Now, how this can be leveraged by hackers is that they will have a bunch of scenarios which they know for a fact that don't exist on your platform or your application. Right? For example, they could generate random keys for your GET requests in your API and try to bombard such requests on your application. What ends up happening is all of these requests will actually have to go to cache, utilize IO and resources there. Then there will obviously be a cache miss because you don't have those keys and those data points inside cache. You will go to the database, also not find anything there. But all this is doing is unnecessarily burdening your cache and database resources. Okay? How can we solve this? Right? Bloom filters are a good way to be able to venture into solving or begin solving this problem. How? You will basically create a Bloom filter with all the entries that are present at a given point in time in cache. And you will always query the Bloom filter first, whether you should actually be going to the cache or not. If the Bloom filter says with guarantee that the data you are requesting is definitely not in the cache, which we just realized that it can do so, then we don't need to go to cache or to DB. We can right away from the application layer respond to the request saying that we couldn't find any data point requested. Right. So that's how we are right now trying to solve one issue around security for our applications. So I'll briefly go over the kind of takeaways you can have for this talk. Right? Measure what you would want to improve, be it system performance or cloud costs. We did it pretty extensively before even talking about any sort of performance optimization or cloud cost optimization. Right? Network round trips are costly, so try to optimize them as much as possible. Understand the pricing of cloud services that you're depending on. Any business critical flows that are heavily dependent on cloud services, understand the pricing and the availability constraints there in order to be able to plan your business continuity well and also to save on costs. And lastly, we also touched upon probabilistic data structures being a useful niche use case where you can query large data sets in real time where approximate answers are acceptable. I think with that, these are the references that I have. The slides will be available to you after the talk as well. So feel free to reach out to me on LinkedIn or visit any of these links in the references. Thank you.
Much. Thank you so much, Aayush, for that wonderful session. So attendees, if you check the schedule, we have other sessions up next, so you could go ahead to them. There are some questions in the Q&A section. While we don't have time to answer them, Aayush, please feel free to go there and reply to the questions individually. Thank you so much once again. Bye.
Thank you. Bye.